Well, I suppose it's customary to start with where one is born and one's early childhood. In my case, I was born in Missouri, and my father and mother then moved to Chicago when I was about 3 years old. My father was a math teacher in the Chicago public high schools, essentially all of his career, and I think that he's a person who's had quite a bit of influence in what I've done. As I look back on my career, I suspect that it's probably like that of many other people. It's a sort of a series of happenstances and accidents, people that one happens to meet, and all kind of circumscribe of what's going on in the country at the time. I was always an omnivorous reader, and while I was in high school, I would take out all kinds of books and look at all kinds of things that might be of interest. My father encouraged us, I have two younger brothers, to try out various things to see what we might be interested in. And one of the things he did was to buy me a chemcraft set, home laboratory chemical set. And I suspect that many of the chemists of our generation were started off with something of that sort. That led to the acquisition of additional chemicals that were discards from the high school chemistry laboratory, to making of fireworks, which is also something that I imagine many of my colleagues have gone through. I found that the local drugstore stocked potassium nitrate, which is a rather unusual thing to find in a drugstore. You wouldn't find it these days. But apparently it was used to some sort of medicine for horses. And the local druggist, I remember one time, asked me, did my father have a large number of horses that seemed to need this particular medicine? So I was rather careful to change my source of supply. But being able to play with these things, try out experiments, to have the freedom to do it, they got me interested in chemistry. I'd say that one of the big turning points in my life was when I won a national scholarship to Harvard after graduating, or the senior year of my high school. And it's hard to believe at that time, but Harvard, before World War II, was essentially an Eastern school. And it was trying to branch out, become a nationally known school. And of course, people nowadays would wonder, was that really true? But it was. But one of the ways of doing it was to develop a scholarship program to try to attract people from the Midwest and Far West. This was their so-called National Scholar Program, which started in the early 30s. And this was a magnificent opportunity, which I happened to get. Harvard would give a 4-year scholarship, all expenses paid, beyond whatever the family could contribute. And since my father had 3 children and was a public high school teacher, that didn't amount to very much. So off I went to Harvard with 4 years guaranteed, provided I kept my grades up. And at that time, I knew vaguely that there was school Harvard in the East. There was also Yale and Princeton. I wasn't quite sure which one was where. But anyway, it was this great opportunity, which... sorry.
No.
Oh, okay. Which really had a major influence in the rest of my life. The Harvard at that time was, again, a little hard to believe, very strongly liberal arts, of course. The scientists were regarded as being sort of below the salt. If you sat at the table with the tutors in the house, why they liked to make puns in Latin, and those of us, of course, who didn't understand Latin just had to kind of shrug our shoulders. And nowadays it's almost completely reversed. The humanists are are very much worried that science is taking over the place, sort of. Anyway, it was, I realized that here was an opportunity not only to learn chemistry and science, but also to have a chance to see what the rest of the liberal arts were about, so that we were encouraged to take or listen in on various other subjects. So I either took or listened in on subjects in art and history and so forth, which was, again, a very exciting thing to somebody who'd grown up in a public school in Chicago. The chemistry was a good quality chemistry for the day. One of the people who was teaching advanced organic chemistry was Bob Woodward, who later went on to win the Nobel Prize. He had received his bachelor's degree and doctor's degree from MIT simultaneously, and then was offered a job at Harvard. But Harvard, in those days, would not make a person an assistant professor, regardless of how they came with genius all over the shirt. So that he was an instructor, and that didn't last very long. He got promoted. But again, that was interesting to have an opportunity to work with him. I did a senior project with him on synthesizing diethylstilbestrol, a hormone, and to see how he thought about chemistry and how he did his research. Again, was an interesting input. Then I graduated from Harvard in 1942. The war World War II had just started, and everything was, of course, very much upset. None of us knew what was going to happen. The nation was slowly cranking up for the military. A classmate of mine, Bill Reed, and I had taken a course at Harvard our senior year, which was called chemical engineering. Now, Harvard had no chemical engineering department. As far as they were concerned, this one course was chemical engineering. It's what we now call unit operations. And it was given by Bill McAdams, who came from MIT to give it. Harvard chemistry department had always recognized that although they were a fundamental basic science, they needed some input of an applied nature in their curriculum. And McAdams had come down for a number of years to give this course. Well, I found this fascinating because this was a practical slant that I had not seen before. McAdams was well recognized throughout the nation, probably throughout the world, as an expert heat transfer. And he would show us how you might design heat transfer equipment and the kinds of adjustment factors one would put in to make the results come out correctly. So anyway, when I graduated from Harvard, my classmate Bill Reed, who had taken the course with me, was very much interested in going into chemical engineering. And he had two brothers that were chemical engineers. Bill McAdams was very eager to get us to come down to MIT. And so he offered us research assistantships, teaching assistantships. Those days, deferments came 6 months at a time, and for a year or two, deferments were granted almost automatically before the armed forces had a chance to really expand. So we went down and began to try to figure out what chemical engineering was all about. I would say another influence was I had a job during junior and senior year at Eastman Kodak in Rochester, in which I worked out in the distillation plant in Kodak Park West. And that in turn also showed me some of the things that were done in industry. So all those things kind of combined to direct me more to chemical engineering from the chemistry background. And that's been a very positive influence in my career, the combination of chemistry and chemical engineering, so that I've always had this ability to say I was a chemist when it was important to be a chemist, and say I was a chemical engineer when it was important to be a chemical engineer. Well, taking courses at MIT didn't last very long with the war coming on, and pretty soon I found myself involved with a project to help develop a new way of making poison gas, phosgene, so that during the the time of the 60s, when students were very much against any association of the university with the military, I was rather careful not to tell them that my master's degree was on a way of making phosgene. Basically, it was a way of synthesizing it under pressure so that you could be liquefied at atmospheric temperature. This avoided having to build expensive compressor equipment. This was a pilot plant that was built in one of the buildings at MIT with a group of maybe 15 or 20 of us that were running this. We were supposed to make about 15 pounds an hour of phosgene. We carried a gas mask at our side at all times. And for the concern at that time was that the Germans might use poison gas, and we needed to be ready to retaliate if it was necessary, and to make it on a large scale. Well, the instructions we had were that if there was a leak or a spill, and this unfortunately did occur from time to time, liquid phosgene pouring out on the floor, that if you were breathing, you should stop in the middle of your breath, whip out the gas mask, put it on, and then you complete that breath. So this was an interesting introduction to chemical engineering as it was played out. But that went on for a while, and then MIT took on a larger project, which was under Tom Sherwood, professor of chemical engineering. I'll talk a little bit about Tom later on. The genesis of this was to develop a new way of propelling Navy torpedoes. Before World War II, all Navy torpedoes were propelled with a system that consisted of a tank of compressed air and a tank of ethyl alcohol. And the two were pushed together under pressure into a combustion chamber. The combustion gases drove the turbine, and then the turbine drove the propeller, and off you went. Essentially, it was a miniature submarine with a warhead on the nose of it. A big limitation on the range and the speed of the torpedo was the fact that you were carrying all this inert gas, nitrogen, in the form of compressed air. And it was obvious that if you had a more concentrated source of oxygen, well, you'd be much better off for this purpose. Concentrated oxygen was a possibility, but oxygen reacts with grease and oil so readily that it was regarded as being extremely hazardous. So instead, the Navy, in great secrecy, began to develop a way of using concentrated hydrogen peroxide in place of air. And as the war began to crank up, they wanted to get some additional input in new ways of doing this. So a substantial program was set up at MIT with Tom Sherwood as the head of it, and he asked me to direct a part of it under his supervision. To the United States at that time, concentrated hydrogen peroxide was something about 48%. This was regarded as being so hazardous that the concentration plant was built in a little island in the middle of Narragansett Bay, which was next to the torpedo station. So in case it blew up, that it wouldn't take much of the station with it. And later, we discovered that the Germans were way ahead of the United States. They were routinely using 85% hydrogen peroxide for a number of purposes. But my part of the project was to try to develop catalysts for decomposing hydrogen peroxide, to test catalysts that were made elsewhere. And so that was my introduction to catalysis. The program went on, and about the time that the war really began to be very intense, late 43, early 44, much more effort was put into this, particularly as information began to trickle back from Europe, that the Germans were way ahead of us on this. The Germans were using concentrated peroxide to launch their V-1 bombs against London, to drive the pumps for the V-2 rocket. They even had a small interceptor plane that ran off of hydrogen peroxide, so that our whole effort went along very rapidly, and I was given deferment to keep on this. Then, towards the end of the war, the Navy, realizing they were far behind Germany on this, asked if MIT would take on a program of research. And by present day standards, this was sort of the researcher's dream world. We were given money by the U.S. The Navy Bureau of Ordnance. I think it was something in the order of $200,000 a year, which in present day terms would be, maybe $1 million, $1.5 million a year. The program was nominally under Tom Sherwood's direction, but he became Dean of Engineering in 1946, and he kind of turned the thing over to me. Hoyt Hoddle, another professor, was supposedly in charge. He had some other things to do than the fact I was running the program. And this was really pretty heady stuff. Here I was, a kid of 20, 25 or so, with this budget of, which would now be $1.5 million or so a year. And I had a group of about 30 people working for me. We were looking at new ways of making peroxide, determining physical properties of peroxide. The way, every year I had to put in a proposal. And the proposal consisted of 2 paragraphs, really, to the Navy Bureau of Ordnance. Said, here's what we think we'd like to do, and it got stamped and the money came back. Well, of course, that was too good to last. But it went on for 3 or 4 years, and then the Office of Naval Research got started, and we were sponsored then for a while by the Office of Naval Research. Well, to go back a little bit, the department gave me a doctorate degree, and I use the word gave somewhat advisedly, in 1946, on the basis of the various things that had been done during the war. And as Tom Sherwood said, well, you've had much more experience than anybody would ever have with a normal doctor's thesis. Why, we think we deserve it. So I wasn't going to argue about it. At the same time, I'd done some theoretical work on ways of calculating performance of rockets by a generalized thermodynamics approach, which was very useful, or could be very useful in those days, because we didn't have the rapid computers. All these calculations had to be done by hand, so that graphical techniques came in to be very, very useful. And in 1949, I wrote the first book, which I was involved with Hoyt Hoddle and Glenn Williams, called Thermodynamic Charts for Combustion Processes. And Hoyt, who was a meticulous, careful mathematician, had done this for air-breathing type engines, and so we put together his and mine. And the book was, I think, quite useful for about 10 years, and then the methods of calculation came along that could be done rapidly for each purpose that was needed. So anyway, that takes us down into the 50s. With this work going on hydrogen peroxide, I decided with 2 of my colleagues that it was time to write the book. This was to have everything in it that anybody needed to know about hydrogen peroxide. And so with the innocence of youth, we decided we'd do this. The American Chemical Society said they'd publish it as a monograph. And we did. It was a monstrous 650 pages or something. And actually, the timing was very good. This was published in 1955. By then, all the physical properties had been developed. The new methods of manufacture were now known, much of it from German sources that were available after the war. And that book has stood up very well. This is now 33 years later. It's still referred to quite a bit. The multi-volume Gemällen, which has all from the German sources, which treats various chemicals, has extensive references to our book. It was translated into Russian by a Russian professor who wrote me, I think around 1957 or 58. And in those days, of course, the United States and Russia were very suspicious of each other, and we didn't know quite what was going on over there. But one day I got a letter from this Russian professor who said that he'd been commissioned by the USSR, something, or the committee, to translate our book into Russian. Please send him a copy, period. That was it. And so we turned it over to the American Chemical Society, and I think they worked out something. Anyway, by the mid-50s, it became evident that we'd done most of what needed to be done on hydrogen peroxide. That we'd looked at different manufacturing processes. The understanding the physical properties. We knew we'd done a lot of work in catalysis and had published a certain amount on that. So I began to look around and think, where am I going to go from here? I can't spend my whole life on this.
Who directed your research with the Navy? Who was the contact there?
The Navy person?
Yes.
That's hard to say. There were people at the Bureau of Ordnance who kind of came and went. Many of them were line officers who had a tour of duty down in Washington. And as a matter of fact, this was interesting. One of the people we dealt with let me back up a little bit. Up to World War II, every torpedo used in the U.S. Navy was tested at the Naval Torpedo Station in Newport, Rhode Island. It was run up the bay just to be sure that it ran, and then it was tinkered with until it ran properly. And we got to know, for example, a submarine captain who had been off in the Pacific on his tour of duty and then was back at the naval station. We learned about torpedo fuel. Being ethyl alcohol, of course, it was tempting for Navy people. And the Navy, to get around this, would put a little crotonaldehyde in the ethyl alcohol, which would cause an upset tummy. And then they put a little bit of red dye in it. But one of the Navy torpedo men that we used to work with just said that it was a well-known technique in the Navy that what you did, you took a loaf of bread, you cut off the top and the bottom, you ran the torpedo fuel through the bread, and of course all the dye remaining behind, this clarified it. They thought that took care of it. Then they drank it, and they'd get very much upset, but the ships were always rocking up and down anyway, so that they didn't attribute it to the ethyl alcohol. So there was this contact with reality, which came in a way that probably more so than most of our students would have today, even through summer jobs and so forth.
Well, I asked because Brunauer of BET was managing a group in the Navy on high explosives and had Einstein as a consultant who wrote a letter on propelling a torpedo.
We were turned pretty much alone, and actually, when the Allies got into France, began to move through France, Tom Sherwood, who was part of the Office of Scientific Research and Development, was asked to go over to France to look at new developments. And I was kind of left behind to kind of run this operation. The people were spread so thin that a young squirt like me was given responsibilities far beyond anything that it would have these days. And he wrote back reports that were, of course, stamped top secret at the time about discovering tank carb hydrogen peroxide in a marshalling yard in France and various other places, so that we got a lot of our guidance on what to do from reports that were coming back after the Allies had gotten into Europe. But anyway, you can't take one topic like that and spend an entire lifetime on it. So that I would say that about the middle 50s, by the time we were writing the book on hydrogen peroxide, that sort of an offshoot of that was one of the ways of making peroxide we considered was through the partial oxidation reactions of hydrocarbons. We can make hydrogen peroxide and thought we might pull up a side stream, make peroxide, and then do some other things. That got me interested in combustion problems for a few years, but that didn't last too long. Again, Tom Sherwood's name keeps on running back through this. He was Dean of Engineering from 46 to 53, and then he got tired of administrative work. He was a person who was genuinely interested in teaching, interested in research. Came back to the department in 53, and he'd been an expert in mass transfer, well known throughout the world as an expert in mass transfer. And he got sort of interested in the interaction between mass transfer and chemical reaction. And this was a topic that got to be quite a hot topic in chemical engineering community in the late 50s. But I'd say that one of the influences of Tom Sherwood was, again, this interest in practicality. He was a good theorist, but he only used the theory where he could see where it might lead. And he got me sort of interested in some of these problems of diffusion, mass transfer. And so finally we wrote a little book together called The Role of Diffusion in Catalysis, which was published in 1963. And I remember that my son, who was, he was 8 years old at the time, he knew that Dad had written this little book, and he used to refer to it as The Role of Confusion in Catalysis. And I always thought, you know, he is wise beyond his years. And I think after we laughed at him once or twice, he used to say it deliberately. So there was a period there where I was working with Tom Sherwood. We wrote this little book, which was, again, very timely, I think. Again, Tom's influence was to try to put in material that people in industry would find useful. Well, after that, in the 60s, he went on to some other things, but he'd gotten me interested in some multi-phase reactor problems, particularly trickle bed reactors, where you have a liquid and a gas running down over a catalyst. And then also slurry reactors, you have a pot of liquid with a catalyst in it. So I began to look at some of those problems. The contacting in trickle bed reactors, then in turn, at the same time, I was trying to follow up this theme of how one solved practical problems in industry. With Tom's background, I began to delve more deeply into ways of predicting diffusion in catalysts. Not so much from the theory, but in terms of, okay, you've got a catalyst here and you make some measurements on it, what is the diffusion rate in it? So that I had a series of theses then on measuring diffusion rates, correlating it with the properties of the catalyst, and that led to the fourth book that I wrote, which is called Mass Transfer in Heterogeneous Catalysis. That, in effect, was a greatly enlarged and expanded version of what Tom Sherwood and I did in '63. Now, by that time, Tom was nearing retirement, and instead of staying at MIT, decided to go to Berkeley. His wife, Californian, and I felt that properly he should be a co-author of the book, even though I'd written most of the second edition myself, but he very generously said, well, I can't claim any credit. Put your name on it. And I think he's a man in our chemical engineering department who may be somewhat unsung, that he was well recognized from the colleagues of his day, and the newer generation perhaps doesn't know too much about him. I think he had a very strong influence in the department in a very quiet way. He wrote many books, liked to write, wrote papers, and had a steadying influence on the department.
How would you describe him as a person?
Slightly blunt, outgoing, very factual, warm-hearted, a keen sense of the overall chemical engineering community. He had written a book on absorption extraction back in the 30s, a book on applied mathematics. He then was active in the war, and he had considerable consulting experience. He worked with Unical for a long time. And I think that he brought back from that a number of problems he could see in industry. And in turn, he would try to encourage younger people to look at some of these. So I first got interested in trickle bed reactors because he came back from his consulting with Unical and said, gee, nobody there knows anything about how these things work. Maybe we ought to do something about it. So that was, I think this again was a theme which ran through other people in the department. Warren K. Lewis, who's our famous chemical engineer, used to talk. He had a farming background. He used to talk about getting the hay down to where the horses could eat it. And the same way, it was the same thing in the textbooks, that we were not ignoring theory. We were pushing theory just as far as we could where it was useful. I think this has been a theme that I've thought was important in our research and our teaching, that we're not going to be empirical on one hand. On the other hand, we're not just going to crank out mathematics for the sake of cranking out mathematics. And the book, Mass Transfer and Heterogeneous Catalysis, again, I was following, I think, Tom's approach of having a number of illustrative examples, real cases, real data, and then analyzing it by the methods we developed. So that took us into the 70s. And I'd say from there I got into these multi-phase reactor problems. I finally wrote a review paper called Trickle Bed Reactors in 1975. As far as I know, that's the first general review paper that appeared anywhere, I think anywhere in the world, on trickle bed reactors. Looking back at it, it's surprising how little was known about them now. What was known about them then. And now there's books on it, books on it. And I've gotten out, there's too much competition. Too many other people are in the field, so we go on to something else. So that book was also translated into Russian. Then I suppose the next thing that comes along is the energy crisis of around the late 70s, and the sudden jump in interest in synthetic fuels. One of the things that I heard about was Fischer-Tropsch synthesis. I had a background in liquid phase reactors, so the opportunity came to pick up the research activities in Fischer-Tropsch synthesis, and I saw that practically all the other work had been done on fixed bed reactors. I thought, well, let's see what can be done in the slurry reactor. Practically nothing had been done, something different, something new, and there's some advantages to it as a way of controlling the temperature of reaction. So we got some support from the Department of Energy, and that started off a program on Fischer-Tropsch synthesis that's now been going for about 10 years and is still going. But the theme that goes through all of this always came back to catalysis, applied catalysis, using catalysts one way or another. And I'd given courses, a number of courses in industry, in mass transfer and catalysis and so forth. And I'd begun to accumulate notes in catalysis. I found catalysis terribly confusing, and I think a lot of other people did too. On the one hand, there was a theorist who had these explanations for everything that seemed to happen, which were good after the fact, but didn't seem to have much predictive power. And then there were people in industry that seemed to know how to make the catalyst, but they either didn't know quite what it was and made it good, or if they did know, they felt that they knew which side of their bread was buttered and they weren't going to tell us. So I began to try to put together a set of notes which was somewhere in between the two, which was catalysis as I saw it being practiced, with the theoretical background that seemed to give some guidance that was useful. And then that finally ended up in a book that I published in 1980 called Heterogeneous Catalysis in Practice. And as I said to the publisher, which was Burrell Hill, I said it does take a bit of chutzpah for a professor to tell people how something is done in practice. But it's been well accepted, and the industry people say it's been very useful. So I now look back at it, and I see a lot of ways in which that needs to be changed, modified, brought up to date. The theory's come along quite a ways in the last 10 years, so that I'm now working on a second edition of that, in which we can now go back further into what one can learn from X-ray diffraction, surface spectroscopy techniques, infrared, and so forth, that is really useful, really useful. So as one moves that way, I think there's a need to integrate the theoretical, those aspects of theory that are useful, and at the same time that the theorists know that there's some of the realities of how you make catalysts, and that economics does come into making catalysts, that it's like making another chemical, that there's costs involved and techniques and that one must pay attention to.
What would you say is the biggest change you've seen in catalysis over the years that you've been in it?
Well, that's a little hard to say. The catalysis community has grown greatly. I think that one of the big changes has been the use of various kinds of instrumental techniques for characterization of catalysts. If you go back to World War II and thereafter, the Brunauer-Emmett-Teller method of determining surface area had been established, mercury pore symmetry techniques have been established, but the surface characterization techniques have really come along since then. Use of Auger, for example, microprobe analysis for characterization of the distribution of active ingredients across a pellet. In one sense, almost every new instrumental technique has a potential of being useful. The problem is that they're out there, and there's dozens and dozens and dozens of them. And the practical person has to kind of work his way through them. So many of the instrumental techniques operate only at high vacuum, and at a high vacuum, of course, surfaces may be different than they are under reaction conditions. Another characteristic is that so much of what's done from a more fundamental point of view is done on plane surfaces. Once one gets into a porous catalyst with things in the interior that the surface techniques don't reach, you can bombard the surface with electrons, and they only come out of the top 20 angstroms, but a lot is happening in the pores that go down deeper than 20 angstroms. So again, it's a matter of trying to sort out the extent to which the fundamental techniques can be useful, what are their limits, and in this sense, it's an interdisciplinary activity. One tries to keep up with what the surface scientists are doing, the materials people are doing, and learn enough about what they're doing to see where it might be applied.
Did you get to know Dr. Thiele very well?
I knew Thiele a little bit. Thiele, of course, for whom the Thiele modulus is named, wrote this, I guess you really would call it pioneering paper, published in 1939 on the effectiveness factor of the catalyst, which has to do with the extent to which the interior of the catalyst is available for reaction. And it was a marvelous paper. He was a fine gentleman. He of course was also known from the Cape-Thiele diagram, which is well known in the chemical engineering field. One of my doctorate students, George Roberts, was doing a thesis with me about 20 years ago, and he was doing some calculations under my supervision on effectiveness factor. Went back to Thiele's original paper, and he couldn't follow the derivation. The answers seemed to be all right, but there seemed to be some mistakes. So again, with the freedom of youth, he wrote Thiele a letter and said, at this time Thiele, who had been with the Standard of Indiana, now Amoco, had retired and was teaching at Notre Dame. And he wrote Thiele a letter and said, Dr. Thiele, there seems to be some mistake here. Can you kind of straighten me out? Well, we learned later that Thiele he kept every piece of paper which he ever written anything, and so he apparently went back through his files that he had saved and wrote back a nice little letter to George Roberts and said that indeed Roberts was correct, that there was a mistake in the derivation, but wasn't the answer correct? And then there was a PS. Don't you think it's a little late for a letter to the editor about this? So he's, you could say in the sense that so much of what's been done since is really kind of lily-gilding, but it's a matter then of generalizing some of the things that he did.
Did you get to know Dan Kohler? Who?
No, I never knew Dan Kohler. Dan Kohler was publishing in the same area about the same time, and Zeldovich in Russia was. And curiously enough, apparently no one of the three knew about the other's calculations. Dan Kohler was doing a lot of work on the mass transfer effects, and there's a whole series of Dan Kohler numbers in the literature that refer to mass transfer effects, not only for a single pellet, but also for pacted.
How has funding for research changed over the years since you started?
Oh, it's gotten more and more difficult. I think that one of the problems we're seeing, well, there's various problems, but one of the problems is that in chemical engineering, the number of people is growing. The number of people on the faculties are growing. The funding in terms of buying power is about constant, so you have an increasing number of people competing for, in effect, the same pot of resources. I think that's one factor. I think another factor is that the universities are becoming somewhat more dependent on outside funding to run the research program, so there is pressure on the younger faculty to get going on a research program, and perhaps a little more pressure to try to develop new and novel things that might look good to a granting agency rather than working on topics that might be more of concern in industry.
What was it that kept your school interest in industry?
Our school's interest? Well, MIT has had a long tradition of this. It was started out as it's an institute of technology. It's almost by definition, it's been the concern with industry. We, in our particular department, we had a research laboratory of applied chemistry way back, starting around 1920 and so forth through the 30s, with where work was done for industry that far preceded present industry-university collaboration. Also, some of the famous people in our department, again the names of Warren K. Lewis and Ed Gillen come to mind, were consultants to industry. Lewis and Gillen were instrumental in introducing the fluid cap cracking process to a standard, what they call Jersey, standard New Jersey, now known as Exxon. And in effect, they did something that's almost inconceivable now. They introduced a completely new process to industry. So that we had this tradition of that it was not only perfectly all right, but indeed highly desirable to have contacts with industry. Lewis and Gillen were consultants, expert consultants, and it was felt that within limits that doing consulting for industry was a desirable action. It's kind of like if you go to medical school, do you want to learn surgery from somebody who's never operated? So that I think MIT established some of the norms that now are accepted around the country. For example, that 1 day a week is a reasonable figure to say that you spend that amount of time on your own activities, by which it's meant outside activities. And that could be not only consulting, but acting on advisory boards for industry, for government. And I did quite a bit of that back in the 50s, when we were more concerned with some of the problems in the military.
How do you see this question of the applied going to military?
Well, this is swung back and forth depending upon depending on the times. It's remember now that there was a war in Korea in the early 50s, in which there was a concern, perhaps exaggerated now, about having to defend communism, or defend against communism. Then we went up a period of the 60s with the Vietnam War, which I would say probably ill-advised, but at that time it was very uncertain about what the nation should do. We went through a period then in which it was regarded as completely improper to have anything to do with the military. And now we're swinging back. It seems to me there's some sort of a middle position that's appropriate here. Where one can make a contribution to military activities, and we think that they're proper. It's I think worth considering. I think chemical engineering is different than some of the other fields in that we are not very heavily associated with the military. I've really had very little to do with military activities for the last 20 or 30 years. For the research and development that's done in chemical engineering really is pointed mostly towards the private sector.
What has been the biggest change in education that you've seen in chemical engineering?
Well, we've seen swings back and forth, and we're probably in the middle of another swing right now. Right after World War II, there was tremendous expansion of the chemical industry, the petrochemical industry. World-scale plants were being put up. The chemical engineers came out of the World War II smelling like a rose, so to speak, that they'd shown that they could scale up by enormous factors the synthetic rubber program, high-octane gasoline for propeller-driven aircraft, which we have to remember that there were very few jet planes in those days, if any. The work leading to the nuclear energy atomic bomb, although we can deplore that now, that was a very important factor during the war. So there was a period then of emphasis on scale-up techniques, design of large plants. I think that there were waves that kind of swept through it. There was a very important wave that came from Amundsen and his colleagues in Minnesota of applied mathematics, which at the time was probably quite desirable. The chemical engineering had been very successful by a sort of enlightened empiricism, and Amundsen brought a rigor and a methodology which was very important. The problem there is, like all innovations, it tended to go to extremes, and that there was a large number of people that came through under Amundsen and his colleague Eris, who then went on to populate other schools and began to, as faculty people, to do applied mathematics, sort of for applied mathematics' sake. There was another important innovation from the University of Wisconsin under Bob Byrd with his colleagues Stewart and Lightfoot, which led to the development of heat mass and momentum transfer as a unified subject. along with this, then there was sort of a swing to more theoretical actions. There was a big emphasis on so-called engineering science, which never has been really completely defined, but there seemed to be growing in more and more faculty people who were getting divorced from industry, that weren't seeing where the problems were, but were doing some nice material that might be useful. We don't know. Chemical engineers have always said that they differ from other engineering schools in having the space in chemistry. And some of our colleagues, indeed some of our deans, have said they've looked around, they didn't see much of this in chemical engineering. And I think to some extent this has been true in the United States more so than in Europe. In Europe, the chemical engineering tradition did not exist. There was the Verfahrensingenieur of Germany, and chemical engineering kind of grew out of chemistry. In the United States, on the other hand, chemical engineering grew out of the petroleum industry, in which the most important problems really were separations, and only later have come along some of the chemistry problems. So I think that we're beginning to see a movement now back more towards the chemistry base of chemical engineering. How far it will move is hard to say. We have the so-called Amundsen report from the National Research Council, which gives hundreds of good things that we should do, and the only matter now is how to put priorities on these and get some more input.
Did you interact very much with Lewis and Gillen about the fluid bed cracking? Or?
When I came down to MIT, which was in 1942, Lewis was was playing with some of these physical properties of fluidized beds. He called it jiggling, and I think that he in turn had picked this up from the so-called Winkler gas generator used in Germany in the 20s and the 30s, and he had a very interesting way of doing this. He knew that this might have some very important applications in industry and Exxon, but on the other hand, he didn't want to do anything that would smack of using a privileged position at MIT to do this, so that he had these thesis students that were working on these fluidized beds. And one time he took the faculty around, showed them what he was doing, and some of the properties of these beds. The thing he left out was the possible application. He thought, well, if they can see the application, fine and dandy, but it isn't exactly necessary for me to say just what it is in detail we're going to do with these. And that was pretty fair.
How would you describe him as a...
Oh, larger than life in every way. The stories just go on for hours and hours, and have been recorded in many ways. He loved to argue. He was a rather dominating person. I think that he had a number of characteristics that I think were interesting as a model. He could take a set of data, he could worry it, he correlate it in a number of different ways, and he would see things in it that very few other people would. And I think this is something that our present generation is getting away from. It's so easy to throw all the data into a nonlinear least squares computer correlation, and can't even be sure who put the program in there in the first place. But it's very easy to overlook effects that way. So that I think we need to be reminded that at least from time to time in research, let's go back to plot X versus Y and see what really happens. He was very good at taking a limited set of data and interpreting it. He loved to argue. And I think there was a way he had of thinking things through. The whole department was very full of very dynamic, single-minded people, strong personalities. So it was a little difficult to grow up in that that environment, but it was a very stimulating one. And the time, of course, was just right.
And who was the one who kept all of these self-assured people happy and able to work together?
Well, Doc Lewis felt that the department, he felt that it was important that people in the department get along with each other, and even though he would snap and snarl from time to time, underneath it all, he had a feeling of it, of family. And Walt Whitman was a department head during much of this time. Walt had been assistant director for Standard Indiana, and in his own quiet way, he kept things going with all these circus performers kind of bouncing around.
What do you think is unique at MIT?
Well, pretty soon it began to sound like somebody from the admissions office was writing a little section for the catalog. Well, again, I think it's several things. I think that one is this close ties with industry and with government. So we've had some sense of where the real problems are developing. It's basically a pretty honest place. We're practically all middle class type people who've kind of gotten there by hard work and brains, so to speak. It's a competitive place, but there's a certain sense of trust, the feeling that top administrators are not trying to do mysterious things that we don't know about. I think that MIT has also been successful in running large laboratories that they got into sort of more or less by accident in World War II. Research Laboratory of Electronics led to other activities in the electrical engineering department. So there's a sort of a cadre of people there that know how to organize large laboratories. There's a certain amount of freedom within the context of doing one's job in teaching and other things. That's been very, very helpful. Boston is also a college university town. I think we profit from our location, although the New England winters are a little tough. But other schools are learning the same tricks, so that we may not be that much different than the others right now.
If you were just starting in catalysis today, what area would you go into?
That's hard to say because I think it would depend where you wanted to tackle it. I think that if there's a generic you and there's a me you, and one could go into it from a knowledge of surface science instruments with some idea of where catalysis is going, what kinds of reactions we're anxious to control. It might be that one could make a mark in a different area, like asymmetric catalysis, perhaps some aspects of enzymes. There's a lot of different aspects that could be covered. I think it's more dependent upon aptitude of the person who's interested. What is he comfortable with? Is he like a hands-on experimenter? Does he like a big piece of equipment? Can he afford, or can he get support for a big piece of equipment? you can approach it from kinetics points of view. No.
I'm out of
That's it?
question.
All right.
Any other areas that,
No, I think that's, I think that these areas that are a mixture of theory and practice, a mixture of empiricism and theory, are the ones that I find fun. That I think that some of us who call ourselves chemical engineers need to, again, kind of remind ourselves of what the chemists do, and that one of the things that most excites the chemist is the unexpected result. So that, again, in our research, we should also have our eyes out for the unexpected result, and that in turn can lead on to some very interesting enlightenment, shall we say. All right?
oh,
Our next paper is paper number 71E,